Okay. So let us just start from the same point where we left off. We were talking a very particular structure of IMPATT diodes, but we also said that we could have different kind of basic structures, variants, which are the same, but they have some specific things that are different. We are talking about this particular diode, which we call reed diode, right? And we talked about its basic structure, how the depletion region will look like, and the electric field profile. So here we stopped in the last class discussing the electric field profile for the reed diodes, where the structure was N plus, P intrinsic, and P plus. Okay, so just to refresh your memories, we had a very different set of N and P type semiconductors here, one very highly doped, one quite moderately doped, and thus the depletion region was also very asymmetric. It was very thin on the N plus side. On the P side, however, it was wide, and it was so wide that the entire P region was not enough for it. After that, we had this intrinsic semiconductor which could not contribute much to stop the depletion region. So the depletion region continued to the entire end of this intrinsic semiconductor, and finally it was stopped by this P plus semiconductor, which supplied the rest of the holes to stop the depletion region at this point. So we marked different regions of this diode. Okay, these are important, so I will just remind you the names once again. Avalanche region is the region close to this junction, the N plus P junction, where the electric field is maximum. Okay, because this side you have huge amount of charges sitting. In a very small area, you have a huge amount of charges sitting, and the electric field is highest at the junction. Beyond that, inside the P region, the electric field decreases, and throughout the intrinsic semiconductor, the electric field is almost constant because the charges does not change much. It suddenly falls off to 0 once you reach the P plus junction on the other side. So the names were like this. Avalanche region was close to this N plus P junction. This entire region starting from this junction to where the final P plus starts, this entire region was space charge region, because that is what we call depletion regions, right? So this entire region was filled by the depletion layer. So we called it the space charge region. This portion is called a drift region, where the electric field is fixed. Why so? We'll discuss that today. This region is called a drift region, where the electric field is fixed or almost fixed. For different structures, you will have either a completely constant electric field or a very slightly varying electric field. So this entire length is called the drift region. And the last P plus region has no purpose other than just stopping the depletion region, ending it from further expanding. So it's an inactive region. It's not of any other use than stopping the depletion region at this point. So here we stopped talking about the field distribution, and today we will mostly talk about the working, that how this thing works. And I told you at the very introduction of IMPATT diodes that here I will introduce, here you will see that the negative conductance, negative resistance region will be introduced in terms of phase. Okay, so the phase lead or phase lag between current and voltage can result into a effective negative conductance. So that is something that we are going to see here. So that working is the main discussion for today's class. Before that, I just introduce you to some of the other structures than which one the one that we are discussing. These are all diodes from IMPATT family. Okay, these are all diodes from IMPATT family, and they all work on the same principle, the same working principle that we are going to discuss today. So don't get surprised that this is not the IMPATT diode that ma'am taught us in the class, because all these are the same things, just a little bit different. Okay, they also have a P plus N or N plus P kind of a highly doped and moderately doped junction. They also have N plus or P plus on one side to stop the depletion region. In between, you can point out that what is the space charge region, how far the depletion region will expand, and where the electric field will be maximum. So you have your avalanche region, your drift region, your space charge region, and your inactive region. So if you have these things inside your device, then you have an IMPATT diode. Okay, so generally only one asymmetrically doped junction. That is the key structure in an IMPATT diode. So these are all IMPATTs. Now let us come back to the particular structure that we were discussing. I will discuss with this one only, but you will be able to extend whatever the discussions we have for the other structures as well. So how this thing works, okay? And for that, you have to constantly remember the electric field distribution that we have discussed in the last class. So just remember the electric field is maximum here. In the p-type region, it reduces and it remains constant throughout the intrinsic semiconductor, drops down to 0 at P+. Okay, just remember this structure. This is going to guide us through the entire working principle. So here, the way I am going to connect my battery in the circuit to make this work is reverse biasing the asymmetrically doped junction. So the N+ terminal is going to be connected with the positive side of the battery. Okay, and the other side is going to be connected to the negative side of the battery. So if I have the junction, the one side that I am sure of, I will connect that to the other side of the battery. So if I have an N+, I will connect that to plus. If I have a P+, and after that I have N, then for the P+ side, I will connect the negative side of the battery. Clear how to select the orientation of your DC battery? So this is the basic biasing that we need to do. Now, if you have this junction negatively biased, that is reverse bias, then what we are looking for is to cause a breakdown at this junction. So as you know, the diode characteristics is divided into different parts, where if you apply a very high reverse bias, then what you see is a breakdown. Okay, so the device that I have here, the IMPATT diode, will work on the reverse breakdown region of the diode. So this is the operating area of the diode. Okay, so I have to connect my battery in such a way so that the junction that I have is at the verge of this reverse breakdown voltage, somewhere here. Okay, somewhere here. So this is the amount of biasing we're looking for. This is the IV characteristics of any general diode. IMPATT's characteristics is not different from that perspective. Okay, from that perspective, they are completely equivalent to the diodes that we usually see. So this is I, this is the current, and this is V, this is voltage. This is the IV characteristics of diode that you are familiar with. Okay, so this is the exponential growth. On the other side, for reverse bias, you know that a very small current flows, but beyond a certain voltage, we see breakdown. And this breakdown region is basically the working region, the operating area for us. So to choose the battery for our device, I will connect this DC battery, let me call it VDC, in such a way that this junction is at the verge of breakdown. That is how I choose the battery. That is how I fix the voltage. So if this junction breaks down, then huge number of carriers will be formed at the high field region. So just remember that this junction is the point where the field was maximum, the electric field was maximum, right? So if you apply a proper voltage, then near the junction, the field will be maximum, and at the junction, a huge amount of electron hole pairs are going to be created because of breakdown. Now, the generated electrons will immediately move to the N region. Okay, they will immediately move here, but the generated holes will travel through this entire region to reach the P+ side and stop there. Okay, and this is what we are going to exploit here. We are going to use this phenomena of transit from this junction to the very end of the device. This is the transit time. We'll use that. You will see. We'll use that, as well as we will use the breakdown to couple them together, and then we will get a system where I can introduce this phase difference that we are looking for. Okay, so this reed diode, we will focus on the two regions. One is the avalanche region, the region where the breakdown will occur, okay, and the drift region through which the electrons will flow. So, or holes will flow, depending on the kind of junction you have. Okay, so this entire region is the space charge region from here to here, as I mentioned. So don't get confused if the diode structure is different. Just pinpoint that what is the space charge region, what is the avalanche region here. So you can simply figure out that if you have a junction, asymmetric junction at this point, then this is your avalanche region. Close to this will be your avalanche region. Okay, and the space charge region will always extend from this junction to the junction where you have this very highly doped end. Okay, so the entire moderately doped or I type, that is intrinsic type semiconductor, through this entire length you will have your space charge region. Okay, so this entire region is going to be your space charge region, and that is equivalent to your drift region. So this is how far your carriers have to travel if they want to reach an N plus side. Okay, so the P plus side will be sitting right next to the junction, but the N plus side will be sitting here, because this entire portion will be depleted of any free charges. Okay, so these carriers have to travel this entire path to get their electrons, the holes, they have to travel like. So fixing our operating area near the reverse breakdown, what we will do is, the first job is to cause the breakdown. Okay, so let us just focus on the working principle here. The first step is called impact avalanche or impact ionization. So here the field, it is nothing but just the diode breakdown. Here the electric field or the voltage will be high enough so that the electrons from the covalent bond of the silicon will break out, and they will start contributing into electric carriers of electricity. So the force of this force associated to the voltage or the field will be so high that it can pull out, it can break the bonds and pull out the electrons from there. Okay, and these electrons will have enough energy that they will collide with other electrons, and they will liberate them from other covalent bonds as well. So it will be like a chain reaction process. So it will go on like a chain reaction. This is how avalanche happens. Avalanche, you know what avalanche is, right? In hills you can see that a small amount of snow can cause a big avalanche, and that is because of this chain reaction. So this kind of a chain reaction will happen, and you will suddenly have a huge amount of electron and a huge current flowing through the device. So this is the phenomena of impact avalanche or impact ionization, or simply avalanche, you can call it. So this will happen. Where this will happen? Near this junction, this will happen. Okay, near this junction, this will happen. So just remember about if I talk about the numbers, then the amount of electric field that we will see at this junction at that time will be several hundreds of kilovolt per centimeter. It's a huge field. It's a huge field that will get created at the breakdown near this junction. Okay, and that is enough to pull out a huge amount of electrons or carriers in general into out. So from their bonds, they will be out, they will be open for conduction. So you can have this huge amount of electron hole pairs generated. Okay, so that is the first step. You fix your voltage such that it happens. Okay, next step is carrier drift. So carrier drift is, as soon as the electron hole pairs get created, they will move to their to the other ways, depending on which way the battery is connected. So just if we look at this particular device, here you see that this side I have positive side of battery attached. So all the electrons will rush towards this side, and all the holes will rush towards this side. Okay, because the negative side of the battery is connected in this side. So electrons will immediately reach the N plus type region, and they will be done. They don't have to travel much. But the holes, they have to travel a long path. They have to travel a long path throughout this entire length. Okay, and that is going to take some time. So this is the carrier drift, when the holes, they travel this long path through the either in PP or intrinsic type semiconductor. And the interesting thing is during this entire travel, because the electric field is fixed for a certain region, you just remember the electric field diagram again. Just think about the electric field diagram again. So you know that the electric field is remaining constant for quite a large length, and this for this entire length, the velocity of the holes is also going to be constant. Okay, so the velocity, with a constant velocity, the electrons and the holes will drift towards their individual terminals, but the holes have a long path to move on. Now we do a trick. If this is up to this point is fine, then what we do is we fix this DC voltage at a certain value just on the verge of the breakdown, and then we attach an AC with the circuit. Okay, and the AC is such that, I mean, the DC voltage is kind of a threshold. So as you go up on the AC cycle, so the AC cycle will be going up and down like this, right? So it's a sinusoidal thing. Okay, so we fix our DC voltage such that here up in the positive half cycle, here the breakdown can occur. Okay, the voltage will be enough, this extra voltage will be enough to cause the breakdown. As soon as this peak is passed, it will be again smaller than the breakdown voltage, so the current will also decrease. So this is very, very important. This is something where I will stop and ask you that if you are understanding this or not. So what my goal is that my AC will go on like this, and the DC voltage will be such that right at this top, when the voltage reaches its maximum, there the breakdown occurs. Okay, so the peak voltage of the AC will be chosen, and the DC voltage will be chosen or paired in such a way that right at the maximum value of the AC voltage, it is enough to cause the breakdown. So are you getting it? Is there any doubt about this, that how we are choosing the DC voltage and the AC voltage? Because this is kind of the key of understanding how this device works. Okay, no doubt. Okay, fine. So as the peak is reached, the breakdown happens, and exponentially the current starts growing. But as the current starts growing, the field, the AC voltage applied here also starts decreasing. So when the current when the voltage is at zero back again, the current is at its maximum, and then it starts falling. So as the voltage goes the other way, the current falls down exponentially and reaches its minima and stops. Okay, so because the breakdown of the device is occurring just for this much of time. So in the x-axis I have time, remember, and the y-axis I have the voltage or the current's amplitude. Okay, so this way the voltage change varies, the AC voltage varies with a maximum value, say VA, and the current pulse gets only created from pi by 2 once the pi by 2 phase is passed on the voltage. Right from that point, the breakdown occurs, the breakdown grows exponentially, and then it falls down and becomes zero again. Okay, so this is how the current is getting created at the junction. By current, I mean the charges per unit time. So the breakdown charges, as soon as the avalanche is occurring, a huge number of charges are being released, and these charges per unit time will give you the current. So this is how the current is getting created internally inside the device. But these charges, I said the charges per unit time, they have to travel through this entire path and reach the other side to actually show you some current if you are connecting an ammeter to the circuit. So if you are connecting an ammeter to the circuit, that will take some time to reach from here to here, because this is a long path and the holes have to travel through this entire path. Okay, so that means the current that you see externally will not exactly start from this pi by 2 slack, but maybe somewhere in between here and here. So because it will take some time, to travel. Now, if by adjusting the length, the drift velocity, the electric field, and the doping level, I can make the current start, the external current start from this point, okay, and introduce another phase lag, introduce another phase lag of pi by 2. This is the pi by 2 phase lag. If I can introduce this pi by 2 phase lag extra by changing this length L, by tuning the drift velocity, by changing the doping levels, okay, these things are in my hand because I am the fabricator. So if I make them properly adjusted so that the current, the external current starts from this point, okay, then I introduce a phase lag of pi between the current and the voltage. So a phase lag of pi means absolutely we have a negative conductance, but we also discussed that anything between 90 degree and 270 degree is fine. Any phase lag between 90 degree and 270 degree is fine. That will give you a negative conductance. So this is how negative conductance comes into the picture, by introducing a transit time delay as well as by creating a huge amount of charges through avalanche breakdown at the asymmetrically created junction. Okay, so transit time delay has a huge role to play here because this basically pushes it beyond 90 degrees. So here you have a 90 degree phase lag created at this point, but that is not enough for a negative conductance. To go beyond 90 degree towards 180 degree of phase lag, what you need is to adjust the time taken from to travel this entire length of capital L. Okay, and these things are controlled by the transit time, which is given by the length divided by the constant velocity, drift velocity. The drift velocity, which is constant because the field is constant, that is for electrons and holes. If I supply you that value and you know that how long your device is, you can control that as well, that how long your device is, then you can basically control tau, right? The time taken, delay. And the external circuit's current, if I call it IT, IE, that is I external, it will be given by the charge seen by the external circuit in the with a period of transit time, right? So that is the amount of charge that reaches per unit time in the external circuit. So this gives you an expression for the external current in the circuit, and this is the transit time. Okay. Sometimes it is also associated with a multiplication factor, that is how many electrons or holes, how much gain of electrons and holes you can expect, and that is given by an expression like this, multiplication factor, that depends on the applied voltage, the avalanche breakdown voltage, and a numerical factor of n that tells you that how many electrons or how many holes, how much carrier you can expect from the breakdown. Okay, so these are the quantities that are in our hand, because depending on the doping level, depending on that how much doped that semiconductor is, the breakdown can be controlled. The length is obviously can be controlled because it is in your hand. Yes, there would be some noise present, the phase that we called phase noise, that it is not exactly 180 degree, which is expected, but it is something between 90 degree to 270 degree, which you get in the IMPATT diodes. Okay, so the external circuit gets this 180 degree delayed phase lag introduced by introduced by the avalanche breakdown, and half of it introduced by the transit time delay, and hence the negative conductance occurs in these devices. Okay, the only problem with IMPATT devices, the major problem with IMPATT devices, I must say, is the phase noise. That is the expected phase lag or phase lead that is expected from here is not always what you get out of it. Okay, it's called phase noise. So it is not always 180 degree. It is something between 90 degree and 270 degree, and it is not always same to what is claimed by its fabricator also. Okay, so it is called phase noise, noise in phase that you expect to see in your device. Okay, so that is the problem that we see in our IMPATT diodes, and this is how they work. So these are immensely used to create microwave oscillations. They just fit this device into a microwave cavity, and they just sync it together, and tuning this length, tuning this voltage, breakdown voltage and stuff like that, because we can actually have this experimental data of how breakdown voltage varies with the impurity doping, amount of doping versus the breakdown voltage for different semiconductors, gallium arsenide, gallium phosphide, silicon, germanium. For everyone, these are experimentally studied. Okay, so this data could be used to control that how much breakdown you get, how many charges get created, how long they take the terminal, and how much phase lag will be there between the voltage and the current, because as we understood that will directly contribute to the negative conductance. Okay, so this is the basic idea of IMPATT diodes. I will stop here, and if you have any questions about today's discussions, please ask.